All right, limits at infinity. Basically, today we're going to be working a lot with our Bobo and Betsy from before and determining the horizontal asymptotes, if any, of the graph of a function. And then determine infinite limits at infinity. Here we go. So this section discusses the end behavior of a function at an infinite interval. Consider this graph over here to our right. So my limit as x approaches infinity happens to be, in other words, when x gets really, really large, like when x is way out here to 1,000,000, what is that y close to? See, that y would be close to 3. When x is way over here at negative 1,000,000 or negative infinity, again, that y value is at 3. If I take a look at this original function right here and did the Bobo or Betsy from Algebra 2 and from college algebra, notice the degrees are equal. So Bobo and Betsy, remember that Bobo meant degree was bigger on bottom, you get y equals 0. And Betsy meant if the degree of the bottom equals top, it's y equals the coefficient. So if you don't remember that, take a minute, write that down. So again, Bobo meant degree bigger on bottom, y equals 0. The degree of the bottom equals top, that would be y equals the coefficients. So, and they're talking about if you were to use a table and your next values were to get really large, like go to 100, go to 1,000, go to 1,000,000, these y's would get really close to 3. And if you took your x values out here to like negative 100, negative 1,000, negative 1,000,000, negative 1,000,000,000, again, these y values would get closer and closer to 3 as well. And again, if you were to divide the bottom into the top, you would end up with 3, and then plus your remainder over that divisor. And since the bottom gets infinitely large very quickly, then that would have been going to 0, and that's why you get 3 plus 0, which is 3. All right, this is just all their fancy notation. So if I have a number over a variable raised to a power and the limit as x goes to infinity, remember that would be like c over 1,000,000, c over 1,000,000,000. Some number divided by 1,000,000,000 would be really close to 0. That's that degree bigger on bottom. It's going to be 0. So we want the limit as x goes to infinity. So this would be 5. No matter how big x gets, that's always 5. And this says minus 2 divided by a huge number squared. So let's say 2 divided by 1,000,000 squared. See, 2 divided by 1,000,000 squared would be super small, so small that that'd be close to 0. Therefore, 5 minus 0 would be 5. So the limit as x goes to infinity of 5 is 5. This limit right here is approaching 0. The bottom is getting faster very, very, very quickly. That's approaching a value of 0. Here, do we have Bobo or Betsy? I happen to notice that we have Betsy. The degree on the top is 1, degree on the bottom is 1. So those coefficients would be 2 divided by 1. So this is equivalent to y equals 2 for that limit as x goes to infinity. Now, if we go ahead and multiply, I'm going to show you all the work for it. Some of you going on to Calculus 2 need to know the proper work to do these instead of doing the Bobo and Betsy. So you would multiply the numerator and denominator both by 1 over x. You want to take whatever the biggest degree is. So in doing that, this would give me 2 minus 1 over x. And then here I'm going to have 1 over x times x would be 1 times that, and this is what we get. And the reason we do that is because now if I take the limit as x goes to infinity, we know 1 over a zillion right here, this would be a big O 0. And 1 over this zillion would be another big O 0. So 2 minus 0 over 1 plus 0, my answer is going to be 2. Now again, going all the way back over here, I already know that I had a horizontal asymptote of y equals 2. See, so really doing all this calculus work, again, if you have to go to Cal 2, please do the real calculus work to get there. But if you don't have to go to Cal 2, understand the Bobo and Betsy, and you've got it. Remember that that denominator would divide into here 2 times, and then you have a remainder over the divisor. That remainder over divisor is going to be approaching 0. So again, that's why you end up with y equals 2 as the horizontal asymptote. And this is a picture of what the graph looks like. You have a vertical asymptote at x equals negative 1. Right there. Horizontal asymptote y equals 2. If we dealt with first and second derivatives, for this part here, we'd be saying the graph is increasing. That would be a positive first derivative. This right here is also increasing. That derivative would also be positive. Second derivative, this first part of your graph is concave up. So that second derivative would be positive. This part of my graph is concave down. That second derivative would be negative. All right, the limits as x goes to infinity. So do I have Bobo or Betsy here? I have Bobo. Bigger on bottom. Degree is 1, degree is 2. Since the degree is bigger on bottom, the answer would be y equals 0 for that horizontal asymptote. So since it was y equals 0, my limit as x goes to infinity would be 0. The real way we're supposed to do it is we're supposed to divide every single one of these terms by 1 over x, divide them each by x squared, the largest degree. So that becomes 2 over x, 5 over x squared, a 3, and a 1 over x squared. Now plugging in infinity for all the x's, 2 divided by infinity, 2 divided by like a million or a trillion or a zillion, that right there is a 0. 5 divided by a zillion squared would be a 0. That is 0. 0 plus 0 on top, 3 plus 0 on bottom is going to give me 0 divided by 3, which is 0. So like I said, those going on to Cal 2, please do this proper work to get there. All right, again, I like to start off with the Bobo or Betsy first. So again, I have the degrees are equal. So if the degree of the bottom equals top, therefore then that's going to be y equals the coefficients, which is 2/3. So this limit, as x approaches infinity, the answer would be 2/3. Now the real work, the biggest degree is x squared. So divide each one of these terms by x squared. So it becomes 2 plus 5 over x squared, 3, 1 over x squared. Limit as x goes to infinity. Again, 5 over that million squared would be 0. That right there would be 0. So 2 plus 0, 3 plus 0 gives me my answer of 2/3 that I said from the beginning. Now this time, if I did my limit as x goes to infinity, well, I don't have Bobo and I don't have Betsy. See, that's that degree is bigger on top. We do long division to get the oblique asymptote. So we'll talk about that later. For right now, we're going to go ahead and do this one the real way. So this one here, we would take the biggest degree, which was x to the third. So divide every term by x to the third. In doing so, this becomes 2 plus 0. This is 0 plus 0. Oh, remember, we can never have a number divided by 0 as undefined. So we would say this limit does not exist. Again, there's the Bobo, degree of bottom, bigger on bottom, y equals 0. The degree of the bottom equals top, y equals the coefficients, y equals 2/3. The degree is bigger on top, divide. So this actually would lead to an oblique asymptote of y equals 2/3 x. So if I actually was to look at a graph of that, if I graph the equation y equals 2/3 x, I know then on this graph, it ends up approaching this line y equals 2/3 x. It actually approaches this original function. And it's kind of cool how it does that. You'll be seeing that in the next couple days and how we can approach the oblique asymptotes. So I wrote out for you so that way you'll have a copy of it. We might have somebody who doesn't have the notes from last year. So there's the Bobo, the Betsy, and the bigger on top. All right, this is going to follow along the same line. And once we define the horizontal asymptotes, the limit as x goes to infinity for this function. The same function, but this time the limit as x goes to negative infinity. Notice these look a little different than the ones that we were used to working with in college algebra. So I still want to look at that biggest degree. That biggest degree is an x squared, but it's under a square root. Well, the square root of an x squared is just x. So basically, what we're looking here, x goes to infinity, so they're all positive numbers. We do know that x equals the square root of x squared. So I'm going to multiply this is big old fancy 1 right here. See, the square root of x squared would be x. So these two right here are actually equal, the numerator and this denominator. So I take that 1 over x with each of these terms. That's 3 and 2 over x. I take this 1 over square root of x squared with each of these terms as well. So 2 and then 1 over x squared. Now the limit as x goes to infinity. That's 0. That is 0. So I get 3 over the square root of 2. And that's my horizontal asymptote also. Y equals 3 over the square root of 2. Now my limit as x goes to negative infinity is just a tad bit different. And the reason it's a tad bit different is because if I was taking a look at negative infinity, this right here then would be a negative number because the x is then less than 0 in this case. That would be a negative number, but the square root of x squared would always be a positive number. So I like to do these I talk about reflected over the y-axis. If we reflect things over the y-axis, we would switch a negative x for x. So if I switch this over the y-axis down, that negative x for x, that becomes a positive infinity, negative x for x there, and a negative x for x here. So that one right there will be squared and back to a positive 2x squared right there. Now, again, the biggest degree was x, and the square root of x squared is x as well. So we do just like we did up above. Multiply each term here by 1 over x, multiply each term of this by 1 over x squared. Again, that's a big 0, that's a big 0, therefore this answer will be negative 3 over the square root of 2. And I want you to take a look at this graph right here. See this graph, this equation for 3x minus 2 over the square root of 2x squared plus 1, that is actually what it looks like. See, this part of the graph right here is concave down. This part's concave up. And this part's concave down. It had two different horizontal asymptotes. So you actually can cross a horizontal asymptote. The horizontal asymptote is talking about when x gets really big or really small, what's happening out at the ends of the graph. Notice it's crossing it here in the middle, and that's okay. All right, so again, this piece, like I said, was concave down. This is concave up. This is concave down. So this one probably has two inflection points. It has one minimum point. And this part here was decreasing. This part was increasing. All right, pause the video and we'll continue here in just a second.